Hi, everyone. Wherever you may be tuning in from, welcome to today's talk. I'd like to introduce my speakers today, Mark Miesling, Kyle Patrick, and myself, Joy Wang, and we are excited to be here. So on the agenda, we'll give a quick intro to graph databases in Amazon Neptune and lead into the star and main theme of this talk, real-world use cases with graph databases at LexisNexis. When we talk about graphs today, we typically see it as an emerging technology. But did you know that graph theory has actually been around in existence for almost 300 years? That's right. On the left here is a picture of the famous mathematician Euler. And Euler used to like to take these walks around the city of Königsberg, which has 2 islands and a mainland connected by 7 bridges, as you can see there. And around that landmass is actually a nice river. Well, one day he wanted to know if there's a path from any one bridge that crosses every other bridge only once and goes back to the starting point. What do you guys think? Is that possible? Well, eventually he came up with the answer that this is impossible, but also he discovered a framework for thinking about these types of problems, a framework for graph theory. And so you may have heard of vertices and edges in graphs. And in this example, a vertex is a landmass on any end of one bridge, and each bridge actually represents an edge. So now let's fast forward to today. Graphs are used in all kinds of applications. Why? It's just a natural way to think about the world around us. I mean, when you see this graph on the left here, you immediately learn 2 things about Alice. Number 1, she lives in any town. Number 2, she works with Bob. So in a graph, the existence of Alice, any town, and Bob are equally as important as how they relate to each other so that you can make sense of the whole data. And so when you see relationships in your data, think graph. Okay, so let's say you do have relationships in your data. What kinds of business problems are well modeled by graph databases? There are actually many applications within social networking, life sciences, IT, pharmaceuticals, and more. But today, we'll focus on 3 popular business applications. The first example is fraud detection. When a credit card transaction comes in, financial institutions want to know, is this likely a fraudulent transaction? And graph databases can help here by detecting fraud in real time based on data such as whether the card number has been previously flagged for fraud, the location of the transaction, or how it relates to previous transactions between 2 parties in the database. But fraud detection isn't just useful in financial services. In fact, online gaming companies can also use graph databases to detect collusion based on player metadata and connections to other players in a game. Next, let's talk about identity resolution. Businesses who interact with their customers digitally often need to answer questions like, is this person who I just spoke to on the phone the same as the person who just emailed me? And graph databases can help resolve identities here by providing persistent IDs that represent all the touch points that your customers may have with your services. And once you have an identity graph, it can also lead to other use cases such as customer 360 applications. Finally, a third popular business problem solved by graphs is knowledge organization, also known as a knowledge graph. Whether you're a business that provides subject matter expertise or you simply have your company data in multiple different stores, you want to know, how can I look at all my relevant data in one location so that I can make the most informed business decisions? Graph databases can link disparate sources of data and the relationships about that data into knowledge graphs. And from there, you can leverage the knowledge graph to improve search results or augment your data with machine learning and artificial intelligence capabilities. So now that we learned a little bit more about what kinds of business problems are suitable for graph databases, I'd like to introduce Amazon Neptune. Amazon Neptune is a fast, reliable, and fully managed graph database service. It makes it easy to run and build applications that work with highly connected data sets. Here are some of the guiding principles of the service. First, Neptune is open. Neptune supports 3 open standards today: Apache Tinkerpop Gremlin, RDF Sparkle, and more recently, OpenCipher. Neptune is also fast and scalable. It can query billions of relationships at millisecond latency. Compute and storage are also scaled independently to meet the needs of your application. In terms of security and reliability, Neptune provides data encryption at rest and in transit, and is in scope for many compliance programs such as HIPAA, PCI DSS, and SOC. Neptune also makes 6 copies of your data across 3 availability zones with automated backup, snapshots, and failover. And finally, easy. You can get started in minutes by provisioning a Neptune cluster and notebook in the AWS Management Console or AWS CLI. Now let's talk about some of the recent innovations from Amazon Neptune this year. At AWS, we work backwards from the customer, and your feedback drives the majority of our roadmap. So first, in caching, we introduced 2 caching capabilities this year: a lookup cache using NVMe solid-state drives, and a query results cache. And both of these caches help to improve the performance of frequent and repetitive read workloads. Our customers asked us for a declarative query language to use on their property graph data. And so this year we launched support for a 3rd major query language on Neptune, OpenCipher. And we also regularly release native query optimizations for the Neptune engine. Machine learning. Announced in preview at the last reInvent, Neptune ML is now generally available to automate the heavy lifting of selecting and training the best ML model for graph data. You can run tasks such as node classification, edge classification, link prediction, and now customers can bring their own ML models as well. In terms of graph visualization enhancements, we open sourced our graph visualization as the Graph Notebook GitHub project late last year. And this year, we added more sample data sets and tutorial notebooks to help our customers get started faster. And we also added key integrations with features such as Neptune ML and Neptune Streams. Our customers also asked us for a better way to manage sudden changes in read workloads. Now, with auto-scaling, a Neptune cluster will automatically adjust the number of read replicas based on your connectivity and workload requirements. And finally, we launched Graviton2 instances, which deliver up to 40% price performance improvements over comparable x86-based instances. And speaking of innovations, we've also been recognized by leading analysts as a leader in this space. Thousands of customers are using Neptune in production today, and here's a growing list of publicly referenceable Neptune customers across different verticals and use cases. Speaking of customers, I'd now like to welcome Mark to the stage and share the awesome use cases they've achieved with Neptune at LexisNexis.
Thanks, Joy. LexisNexis is a legal research company, and our mission is to spread the rule of law around the world by making it easier for legal researchers to get to the data and insights they need to craft the best legal arguments. So in this part of the talk, I'll explain how we've scaled our machine learning using Amazon Neptune, both by getting our machine learning into more places, as well as enabling entirely new kinds of machine learning by getting all of our data connected in the graph. So in today's talk, I'll explain one way that we've made it easier for users to get to the data that they need by building a graph-based recommendation engine. And then I'll talk about how we've shared that graph across the business through an API, and how that's multiplied the value of the graph by attracting new contributors and consumers around our business. So, like a lot of businesses, we collect data from disconnected sources. It's millions of unstructured text documents from law firms, where legal researchers craft their arguments, from the courts, where those arguments are decided and outcomes are provided, and from vendors. So those are external analysts, news publishers, and various other sources. So even though these data sets are disconnected, they do share deep connections in the real world, because a single legal matter might produce documents from a law firm, from a court, and from a vendor. And our users expect to see those documents in one place connected together. On top of that, we have various machine learning, natural language algorithms that we run on those data sets. So for example, we may extract from a law firm document that it's about trademark infringement or advertising or likelihood of confusion. And we have an opportunity to do more and better machine learning of that kind if we have all of this data connected together. So we thought, let's connect and search our data automatically for our users so that they can get that complete picture of what is going on in a particular legal matter without having to connect all that data on their own. And that led us to one of our flagship products, which is brief analysis on Lexis+. And the idea here is that a user can upload their own brief and get a set of recommendations from LexisNexis about similar briefs that might contain legal concepts that they haven't thought of, arguments that might help in their scenario, as well as other opinions that they want to cite that they might have missed. So we built this using Amazon Neptune. And the way that we recommend similar briefs is by connecting our own corpus of briefs to two key nodes. So one of those is legal concepts. So we extract legal concepts from our own corpus of millions of briefs, connect that to each brief, as well as the opinions that that brief has cited. So in legal argumentation, legal researchers cite influential opinions to craft their arguments. And so we connect all of that together in Neptune. So here's how that looks. We have our law firm brief, and that is connected to legal concepts and court opinions. Here's how we built our knowledge graph. So as I mentioned, we start by extracting the legal concepts and citations from millions of Lexis briefs using lots of AWS services, including SageMaker, EMR, and step functions. We represent those concept and citation relationships all together in Neptune. And that allows us to build an app layer on top of that so that when a user uploads their own brief, we query the graph for briefs with similar connections and produce those recommendations for our users, all without users needing to do any kind of manual searching on their own. So that's brief analysis, and I'd love to give you a demo of that now. Let's imagine that I'm drafting this legal brief in the matter of Premier Pools, Inc., v. Premier Pools Management Corporation. And I'm concerned with the defendant's use of the name Premier Pools. I think it's too similar. It might cause confusion. So I've drafted this brief, and now I can upload it to Brief Analysis and get some recommendations about how I can improve it. So in particular, Brief Analysis is going to scan the brief for citations to other influential cases, legal concepts, and provide recommendations of similar briefs looking through the entire Lexis corpus. So here we have our 30 similar briefs that we've found. Each of these briefs shares some legal concepts and citations with my own document. I'm going to look at this appellant's brief here. It looks pretty interesting. It shares some concepts like secondary meaning, likelihood of confusion, and a variety of matching citations. So let me open this brief. And this turns out to be Osaka Japanese Restaurant versus Osaka Steakhouse. Sounds pretty similar to my Premier Pools v. Premier Pools situation. And indeed, this is about wrongful use of the name Osaka. So without doing any manual searching at all, I've gotten to some very relevant content to help me craft a better legal argument. All right, so that was brief analysis, the graph-based recommendation engine. And now I'd like to talk about how we were able to share that same graph across the business via a generic API and multiply the value of the graph across different contributors and consumers around our business. So the first opportunity that we thought of was to connect the law firm briefs and their arguments to the outcomes. Now the outcomes are contained in a different document set, so those are contained in documents from the court. And we have another product called Context that extracts the outcomes of motions, granted or denied, from those court documents and provides analytics around how likely a certain judge or court is to grant a certain motion type based on the historical record of data that we have here. So we thought, how can we connect those law firm documents to their outcomes and kind of really multiply the value and provide something entirely new here? So it was actually pretty easy to add Context, which is that legal analytics product, to the knowledge graph. So remember, we start with these three nodes here, the law firm brief, which is connected to its legal concepts and the court opinions that it cites. We only needed to add two more nodes here to provide this new experience in context. So one of those is the motion outcome from the court that's extracted using NLP techniques. And the other is this legal matter node. So that is the entire legal matter, which might be Premier Pools versus Premier Pools, that encompasses all of the documents produced at different sources that pertain to that matter. So by connecting these together, we can now run a simple query. Starting with a law firm brief, we can see what legal matter it belongs to. From there, we can find the court opinion that might decide its outcome. And of course, we have that motion outcome connected to the court opinion as we've extracted it using our NLP techniques. So I'd love to demo what this looks like in context. Here's one of our Knowledge Graph API endpoints. I'm going to send it the ID of a single document and get back all the other documents in that same legal matter along with various metadata that we've extracted. So here we have defendant's motion to dismiss the complaint, document from a law firm, and connected to that same document, we have an opinion from the court, which refers to a motion to dismiss that's granted. So now I have the outcome of that legal brief, and we can start to put these documents together in the knowledge graph and tell the complete story of this legal matter from motion to outcome. So let's see what this looks like in our product. Here's a key legal argument extracted from a brief. That brief is situated among the other briefs that belong to this legal matter along the bottom here, as well as the order from the court deciding the outcome of that particular motion. So now we can add all of this together as a new consumer to the knowledge graph. We already have brief analysis as a consumer of this pipeline in our Amazon Neptune knowledge graph. Now it's just a matter of adding context as a consumer. And we've just multiplied the value of that graph. We can ship it out to more products and build more complete experiences for our users. We can continue to multiply the value through this API and by adding new consumers throughout the business. So I'll talk a little bit about what kinds of new use cases have arisen just by having this API available across the business and how we've been able to multiply the value with those new contributors. So some of the new use cases around the business that our API is spurring, one of those is even more machine learning. So I mentioned that machine learning powers the graph in the sense that it's a place where we collect all of our machine learning insights and inferences, but it also allows for new types of machine learning based on this connected data. So one of those is currently underway by another data science team, and they're looking at some advanced NLP analytics around the language of particular arguments and how those influence the judicial outcomes, which is enabled by having all this data together in the graph in the same place for the first time. Another use case is entity deduping. So I mentioned that the graph helps us detect similarity, and that's usually a good thing for our use case of trying to recommend similar briefs. Sometimes we have too much similarity, and what I mean by that is we might have duplicate entries in our authority of US attorneys. So we maintain a list of all the attorneys in the United States, and we can detect dupe entries by looking at entries that have lots of shared connections and maybe a similar name. Those are good candidates for those entries actually being the same person. There's another machine learning use case around train and test data separation. So of course, in machine learning, we want to make sure that we don't test on our training data. And the way that we do that with the graph is by making sure that we draw our training data and our test data from separate legal matters. The graph tells us which documents are connected together in a legal matter, and we can make sure that we don't sample from those same sets in finding our training and test data sets. So if a couple of documents come from the same legal matter, they might refer to the same names, the same legal concepts, and we're essentially at risk of data leakage there by testing on the training data itself. The graph helps us avoid that situation. And finally, there's a whole family of use cases around network analytics. So the graph itself can become a product. One of the kind of core use cases there is the relationship of opinions citing other opinions. So some opinions are influential in the law and are very good to cite. Other opinions have been overturned and are so-called bad law, and you want to make sure you don't cite those. So we have a product around that use case called Shepard Citation Services, and I'll hand it off to Kyle to talk about that.
Thanks, Mark. So I'd like to talk about another use case that we have at LexisNexis for the Amazon Neptune Graph Database, and that is our adoption of it for our Shepard Citation Service. So first, let's look at some of the details of the Shepard Citation Service. A core part of legal research is evaluating the validity of any given case ruling or law or regulation, specifically how it's typically regarded by precedent established by courts subsequent to its issuance. So we have a service called Shepard's, which tries to capture all of the details about the citations and the treatment of them, which is to say how positively or negatively that citation treats the subject matter. And with that, we build a graph, which is used to provide information specifically regarding if a citation is considered positive or negative, and what's the trend over time, as well as a top-level signal for anything that we look at that can show if something is overruled or considered questionable or considered well-supported rulings or law. And this has been a core practice in legal research going back for over 100 years, first in print, and then LexisNexis has transitioned it to digital with many iterations of that as part of their legal research platform. And we'll look at one of the previous iterations of that, which was done on a document-based NoSQL service. So as part of that solution, every single Shepard's report was generated as a single large document with all of the citation information kept within it. And so that model is very convenient in some ways, as that co-locates all the data and allows us to run queries against individual documents in order to get details of all the citations, inbound and outbound, that might affect a given document. The challenge with that, however, is given the ever-growing corpus of legal texts and the ever-growing number of connections between them, there's kind of a scaling problem there. There's many documents that are very, very frequently cited, and so they have a very large number of inbound citations. And tracking that means effectively tracking an ever-growing corpus of those relations at a document level. Another challenge there is the method of update. So because all of the details of a citation are stamped into a number of different documents, a single update to a case could have a ripple effect and cause us to repackage and republish a very large number of Shepard's reports. And so this is a practice that over time we've seen as something that has risen in operational costs as we need to fabricate a very large number of these per day. In many cases, it being a single small update causing us to regenerate a large number of reports. So as we've looked at that architectural fit, we've evaluated whether or not adopting a graph database would be appropriate. And so we've modeled this out on Amazon Neptune, and we found that, as you'd expect, porting the citation graph over to Amazon Neptune is a very natural fit for the data, and it allows us to keep the updates far more proportional, such that an update to a single case can be reflected by updating properties on a single vertex. So that eliminates the need to do broad republishes whenever we see updates. And with that, it lowers the overall operational cost of generating all of the backing Shepard's data. So this data actually surfaces in a number of different places in our products. So for one, we have the citing decision analysis, which kind of allows us to view the trend of Shepard citations across a very large number of degrees, such as the jurisdiction of them and how they trend over date. So being able to see which courts have been talking about a particular case or law, and have they been discussing it negatively or positively, is a very powerful feature. Also, when we consider a case potentially overruled, typically there's kind of a seminal ruling that determines that. And so we surface that with our reason for Shepard signal feature, where we also embed in the graph all of the details that come from the editorial side, which can determine what is the most essential ruling that can determine the state of this case. We also have taken this Shepard's graph and used it to construct our Ravel view of our search results list. So this feature allows users to run their own searches across our legal content. When they get back the result list, it's typically in a very flat format, a flat list of results. But with the Ravel view, we can then view the interconnections between these results, such that we can see which documents cite to each other, how those citations have trended over time, and then which documents are very broadly cited, either positively or negatively. We bring all of that treatment data into that graphical view. And further, as Mark has talked about the brief analysis use cases, where a customer uploads their own content. So as part of drafting a brief, that document will typically have a large number of citations within it. And so we also identify those citations and go check the Shepard signal for those citations so that we can give the person who's doing the drafting immediate feedback on the overall quality of their citations. Is it supported law, or is it potentially unsupported law? So an essential part of this process has been building a loading pipeline that can keep up with a very large number of updates that we see per day. So we worked with the Amazon Neptune team to construct a bulk loading pipeline that could generate events coming from our centralized citation database, stream them over Kafka, and then have services that can package that into CSV files that we then ship to S3 and tell the Neptune system to load from there. And that bulk loading allows us to effectively have a very high rate of throughput for loading into the graph with very limited impact on the performance of any kind of real-time queries that we might be running. And that's been essential. We can have up to 100 million graph updates per day. And so this pipeline has been a very important factor for migrating the Shepards to Neptune. So in review, we've looked into the use cases where there's a synergy between our adoption of knowledge graphs and our data science processes, and how we've established a virtuous cycle between the two, wherein the improvements that we make to the knowledge graph help with our data science workloads, and then our data science outputs can be ported back into the knowledge graph to expand the use cases that it's capable of. We've seen how easy it is to add new additions to that knowledge graph that can enable net new use cases, because the open model for a graph database allows it very easy to migrate new features onto it. And then with the various query languages that are available on Amazon Neptune, the ease at which we can create custom APIs that can expose that functionality broadly throughout the organization to, again, bring that intelligence from the knowledge graph into a wide variety of products and fabrication systems. And we've also seen how Amazon Neptune can also be used to remodel the data that's backing some of our production systems and build new customer-facing products using them. And a lot of talented individuals have contributed to these efforts for adopting Amazon Neptune at LexisNexis. So we would like to thank the teams involved. It has been a lot of effort, but the results have been astonishing. So I'd like to thank everyone. And now here's back to Joyce for the wrap-up.
All right. Thank you so much today, Mark and Kyle, for sharing these great real-world use cases on Amazon Neptune. We also learned today that graphs are valuable for all kinds of use cases, including knowledge organization, identity resolution, and fraud detection. And if you find one graph use case, chances are that there are other business problems that can be solved with the same graph.